In this video, we're going to use significance test to investigate the mean of samples and what information we can deduce from those samples. Back in M2, we looked at significance tests with the binomial distribution, and we set up the key steps for conducting a p-value significance test. And those key steps were, first of all, to define the variables. Then we needed to state the two hypotheses under consideration, namely the null hypothesis and the alternative hypothesis. We had to describe the test statistic on which the significance test was going to base its decision. And we had to be able to give the distribution of the test statistic on the assumption that the null hypothesis was true. We then need to state whether the test is a one-tail or a two-tail test. Once we have done that, our fourth step is to calculate the p-value for the test. That is, we've got to calculate the probability, assuming that the null hypothesis is true, of getting a result that is in the tail starting at the observed value. If the test is a one-tail test, then this probability is the p-value. On the other hand, if the test is a two-tail test, then this probability must be multiplied by 2 to obtain the p-value. And the final step is to use the p-value to give the conclusion of the test in context. If the p-value is less than 0.01, then there is very strong evidence to reject the null hypothesis in favour of the alternative hypothesis. If the p-value is between 0.01 and 0.05, then there is strong evidence to reject the null hypothesis in favour of the alternative hypothesis. But if the p-value is greater than 0.05, then the data does not give sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. The tests that we're going to be looking at are going to be using the sample mean as our test statistic. And in the previous video, we discovered that if we take samples of n random observations from a population which is normally distributed with mean mu and variance sigma squared, and x bar is the sample mean of this sample of n random observations, then x bar is itself normally distributed with a mean of mu and a standard deviation of sigma over root n, or equivalently a variance of sigma squared over n. And we could summarise that by saying that x bar is normally distributed with mean mu and variance sigma squared over n. So let's now have a look at an example. When tennis balls from a manufacturer are dropped from a standard height, if the height of bounce h centimetres is measured, then h is a random variable which is normally distributed with a mean of 40 and a standard deviation of 9.5. A sample of 60 balls from a second manufacturer were also dropped from the same height, and the sample mean of these heights was 37.8 centimetres. Assuming that the standard deviation of the heights of bounce of the balls from the two manufacturers are the same, determine whether there is evidence that the balls from the second manufacturer have a lower mean bounce height than the balls from the first manufacturer. So we'll answer this using our procedure for a p-test. So we must start by defining our variables. So let's have mu being the mean of the bounce height for balls from the second manufacturer. We need to state our hypothesis. The null hypothesis is going to be that mu is the same as the mean for the first manufacturer in other words, mu is 40. The alternative hypothesis is that the second manufacturer's balls have a lower bounce height than the first manufacturer's ones, in other words, that mu is less than 40. We need to describe the test statistic that we are using to make the decision and its distribution on the assumption that the null hypothesis is true. Well, we're using the sample mean of the bounce heights for 60 balls from the second manufacturer. And if the null hypothesis is true, then we can say that h bar is going to be normally distributed with a mean of 40 and a variance of 9.5 squared divided by 60. This is most definitely a one-tailed test because we're only going to want to accept the alternative hypothesis if the value of the sample mean is surprisingly small. So it's definitely a one-tailed test. So we've now got to work out the p-value for the test. Now we know that h bar is normally distributed with mean 40 and a variance of 9.5 squared over 60, which means that the standard deviation of h bar is 9.5 divided by root 60. So the p-value is going to be the probability that h bar is at most 37.8. So we've taken the tail to the left of 37.8 to obtain the p-value. So the p-value is the probability that h bar is less than or equal to 37.8, which my calculator gives me as 0.0364. And we can now use this p-value to give the conclusion of the test in context. Since the p-value is bigger than 0.01 but smaller than 0.05, we can say that there is strong evidence to reject the null hypothesis in favour of the alternative hypothesis. In other words, we are saying that there is strong evidence that the balls from the second manufacturer have a lower mean bounce than those from the first manufacturer. Let's now then move on to a second example. In a large factory, the time taken by employees to carry out a certain task is known to be normally distributed with a mean of 116 seconds and a variance which is 68.9 seconds squared. A new training scheme is introduced, and after its introduction the times taken by a random sample of 85 employees were recorded. The mean time for this sample was 117.6 seconds, and the sample suggested that there had been no appreciable change in the variance of the times taken to complete the task. Determine whether this sample provides evidence that the training scheme has resulted in a change in the mean time taken to complete the task. So again, we're going to set this up as a p-test. So we must start by defining our variables. So let mu be the mean time taken to complete the task by people who have undertaken the new training scheme. Our null hypothesis is going to be that there has been no change, in other words, that mu is 116. The alternative hypothesis is that there has been a change. So we are saying the alternative hypothesis is that mu is not equal to 116. Our test statistic in this case is going to be the mean of the times taken by a random sample of 85 employees who had taken the new training course. If the null hypothesis is true, then we can say that t bar is going to be normally distributed with a mean of 116 and a variance which is 68.9 divided by 85. Now in this case we want to accept the alternative hypothesis if the value of t bar is either much more than 116 or much less than 116. In other words, we have certainly got a two-tailed test. We must now calculate the p-value for the test. Now if the null hypothesis is true, then we know that t bar is normally distributed with a mean of 116 and a variance of 68.9 divided by 85, which means that the standard deviation of t bar is the square root of 68.9 over 85. Now we're doing a two-tailed test, which means that the p-value is going to be twice the probability of getting a value which is at least as extreme as the one that we observed. The value we observed was 117.6 seconds, so the tail corresponding to 117.6 seconds is going to be t bar being greater than or equal to 117.6. So the p-value is going to be 2 times by the probability that t bar is greater than 117.6. And if we work that out on using the normal probability calculator on our calculators, then we find that this value is 0.0756. Since the p-value is greater than 0.05, the data does not give sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. So we can say that the sample of employees that we've been looking at does not provide evidence that the new training scheme has changed the mean time to complete the task. Finally, to complete this work, there's an example here that I'd like you to try and work through and take to your next lesson. So pause the video, work your way through this example, and then take your solution along to the next lesson. In the next video, we're going to look at significance tests of the sample mean using a critical region.